Hello my dear students, welcome back to our class. So we started complex numbers in our previous class and we have learned what is a complex number, what is the general form of a complex numbers, and we have already learned that what are the operations related to complex numbers. And in today's class we are going to learn the geometrical representation of complex numbers. We know that real numbers are always represented in a real line. All the real numbers can be represented in this real line. Then how will we represent complex numbers? All the complex numbers can be represented in a plane. And we know that a plane always have two axes, that is x-axis and y-axis. So every complex numbers can be, or every complex number can be represented in a plane, and now we are going to see how a complex number can be represented in a plane. Let a plus ib be any complex number named z. Let z is equal to a plus ib. Then how can we represent a plus ib in this plane? Now we know that a is the real part of this complex number and b is the imaginary part of this complex number, and this a comma b together forms a coordinate. And we learned how to represent a coordinate in a plane, and if this is a in x-axis and if this is b in y-axis, then AB is the point of intersection of these two lines, that is this point. So this is AB. So similarly, we can represent any complex number into the plane by simply representing the coordinates as real part comma imaginary part, and hence we will get a coordinate, and plotting that particular coordinate in the plane will gives you the geometrical representation of that particular complex number. So for example, if 2 plus 3i is z, if z is equal to 2 plus 3i, then 2 comma 3 will give the point corresponding to this complex number in the plane. If this is 1, 2 and 3, this is 1, 2 and 3, then 2 comma 3 is 2 comma 3, intersection of these two lines. So this is 2 comma 3, and this particular point is the geometrical representation of the complex number 2 plus 3i. And look here, we have marked the real part in x-axis. So the x-axis is called the real axis, and the imaginary part, that is 3, is represented in y-axis. So y-axis is called the imaginary axis. So x-axis is the real axis and y-axis is the imaginary axis, and this plane which is formed by the real axis and imaginary axis is called complex plane or Argand plane. So the complex plane which consists of real axis and imaginary axis, which also include every complex number into that particular plane, is called complex plane, and it is also called Argand plane. So Argand plane is a plane which represents all the complex numbers into a plane. So this is the geometrical explanation of complex numbers. So now we have a complex plane or Argand plane here, and let this be the origin, and it is 0, 0, and it represents the complex number 0 plus 0i, and let me call this as O, this point as O. Now let P be a point which represents the complex number p is equal to a plus ib. So this particular point is a comma b. So we have 2 points, the origin and p, in this plane, and we know how to find the distance OP. So OP can be found using the distance formula, that is square root of a minus 0 square plus b minus 0 square. So that can be simplified as square root of a square plus b square. So the distance OP is simply square root of a square plus b square. And we know that for any complex number of the form a plus ib, its modulus, if z is equal to a plus ib, then mod z is square root of a square plus b square. So the modulus of a complex number is the distance of that complex number from the origin. So here P denotes the complex number a plus ib, and the distance of P from the origin O is square root of a square plus b square. So we can generally say that the modulus of a complex number is the distance of the complex number from the origin. Also we know that the conjugate of a complex number z is equal to a plus ib is z conjugate, which is a minus ib. Now let's represent z conjugate in this Argand plane or complex plane. That is, the point representing a comma minus b is the point corresponding to the z conjugate. So a comma minus b. This is a and this is minus b. So a comma minus b means it is this point. Yes, this point is a comma minus b. So this point represents the conjugate of this complex number. So this is the point which represents z, and this is the point which represents z conjugate. So we can see that the mirror image of this point is this point. We have the mirror image of P as the point here. That is, the conjugate of a complex number will be always a mirror image of that complex number in the complex plane. We can clearly observe that if this axis acts as a mirror, then this particular point is an image of this particular point is an image of this P. So that's it. So that is the relevance of modulus and conjugate of a complex number geometrically. We have one more representation of complex numbers in complex plane, that is polar representation. Let's see what is the polar representation of a complex number z is equal to a plus ib. We have one representation that we have learned before, that is representing a plus ib as the coordinate a comma b. The other representation will be like this. Let this be origin, that is 0, 0, and let this point P be the point corresponding to the complex number a plus ib, that is a comma b. Now let OP be the distance from O and P, and we have proved that OP is nothing but square root of a square plus b square, which is the modulus of the complex number z, that is mod z is square root of a square plus b square. Now I am going to name this distance as r, small letter r. So r is equal to square root of a square plus b square. So this is r, and now I am going to define one more component, that is theta. And theta is defined as the angle made by the line OP with the positive direction of x-axis. What is the theta? Theta is the angle made by the line OP with the positive direction of x-axis. This is x-axis and this is the positive x-axis and this is negative x-axis. So theta, always remember that theta is the angle made by the line segment with the x-axis, with the positive direction of x-axis. So if this was another complex number q, if this represents another complex number q and this is the origin, then OQ is our r. That is the distance from origin to that complex number. The distance is OQ and this is the point r. And what will be the theta here? Theta is the angle made by this line segment in the positive direction of x-axis with the positive x-axis. So the angle made by the line segment OQ with the positive x-axis is theta here. So this is the theta here. So corresponding to every complex number, we can find two components, that is the distance from origin to that particular point, which we call r, and one theta, which makes in the positive direction of x-axis. So r comma theta forms another such coordinate which represents a complex number, and this type of coordinates are called polar coordinates. Remember that theta is the angle made by the line segment with the positive direction of x-axis, and r is the distance OQ, which is all, if z is equal to a plus ib, then r will be square root of a square plus b square. So r comma theta forms the polar coordinates of this particular complex number. So corresponding to every complex number, there is a polar coordinates like this, that is r comma theta. Also we have a is equal to r cos theta and b is equal to r sin theta. Therefore z will become, z is a plus ib, so that is r cos theta plus I into r sin theta. So taking r common, we will get r cos theta, r into cos theta plus I sin theta. So this is the polar form of a complex number, and r is the distance from O to the particular complex number, that is square root of a square plus b square. R is equal to square root of a square plus b square, and theta is the angle made by OP with the positive direction of x-axis. Since theta is the angle which makes with the positive direction of x-axis, theta can take values from 0, pi, 3 pi by 2 and 2 pi. So theta is the value, is the angle which lies between 0 less than theta, 0 less than or equal to theta less than or equal to 2 pi. So this is the values which take for any complex number between 0 and 2 pi. So the length of this particular interval is 2 pi. So we can take theta as an angle between minus pi less than or equal to theta less than or equal to pi, and we know that the length of this particular interval is also this particular range is also 2 pi, that is pi minus pi, pi minus pi is pi plus pi, that is 2 pi. So minus pi, an angle between minus pi and pi is also the angle corresponding to a complex number, and this range of theta is called the principal argument. Principal argument. And what is argument? Argument is this theta, the angle made by the complex number with the positive direction of x-axis is theta, and that theta is called argument. And if the value of theta lies between minus pi and pi, then it is called principal argument. So in polar form, we usually write the theta as principal argument and r as square root of a square plus b square. Now we shall solve some problems which ask to represent certain complex numbers into polar form. Now the question asked is to represent z is equal to 1 plus I root 3 into polar form. Polar form is, we know that z is equal to r into cos theta plus I sin theta. And we know that we have the real part a is equal to 1 and the imaginary part b is equal to root 3. And also we know that r is equal to square root of a square plus b square, and theta is an angle between minus pi and pi, which is the principal argument. So since a and b are known to us, we can find r directly, that is square root of a square plus b square, that is 1 square plus root 3 square, and that is 1 plus 3, square root of 1 plus 3, which is root 4, which is 2. So we got r is equal to 2, and we know that a is equal to r cos theta and b is equal to r sin theta. Substituting the values of a, b and r in these equations, we will get a is equal to 1. So 1 is equal to 2 cos theta, which means cos theta is equal to 1 by 2. Again we know that b is equal to r sin theta, that is root 3 is equal to 2 sin theta, which means sin theta is equal to root 3 by 2. We got cos theta as 1 by 2 and sin theta as root 3 by 2. And we know that tan theta is nothing but sin theta by cos theta, that is root 3 by 2 divided by 1 by 2. So 2 and 2 gets cancelled and we get tan theta is equal to root 3. So we got sin theta as root 3 by 2, cos theta as 1 by 2 and tan theta as root 3. Looking into these values, we can easily identify that all the cos theta, sin theta and tan theta are positive, and we know that all the trigonometric values are positive only in the first quadrant. So this is the quadrant where theta lies. So and also cos theta is equal to 1 by 2, sin theta is equal to root 3 by 2 and tan theta is equal to root 3. All these three things happen together at theta is equal to pi by 3. We know that cos pi by 3 is 1 by 2, sin pi by 3 is root 3 by 2 and again tan pi by 3 is root 3. And also it satisfies this condition, theta is equal to pi by 3 lies between minus pi and pi. So we can conclude that the required theta is pi by 3. And also we got r as 2. Since we got r and theta, we can substitute it in this equation, which is the polar form of this complex number. So z is equal to r into r is 2 cos theta is pi by 3 plus I sin theta, that is sin pi by 3. So this is the polar form of the given complex number 1 plus I root 3. So the next question is, represent this particular complex number into polar form, and the polar form is r into cos theta plus I sin theta, where r is equal to square root of a square plus b square and a is equal to r cos theta and b is equal to r sin theta. Now we have r is equal to square root of a square plus b square, and we have to find the a and b, that is the real part and imaginary part from this complex number, and this is not in the standard form. So first of all we are going to make the complex number into standard form, that is z is equal to minus 16 by 1 plus I root 3 is the given complex number. So in order to make it into the standard form, we have to multiply the denominator with its conjugate. So conjugate of 1 plus I root 3 is 1 minus I root 3. So we are going to multiply it in both numerator and denominator. So it will become like this, z is equal to minus 16 plus 16 root 3 I divided by 1 square minus root 3I square. So minus 16 plus 16 root 3I divided by 1 square is 1 minus root 3I square. Root 3 into root 3 is 3. I square is minus 1. So minus and minus get positive. So it will become 3. So minus 16 can be taken common from numerator. That will become minus 16 into 1 minus root 3I divided by 4. So we have 16 and 4 gets cancelled and here it will become 4. So the required complex number is minus 4 into 1 minus root 3I, which can be again written as minus 4 plus 4 root 3I. So this is the general or standard form of the given complex number, where A is equal to minus 4, that is the real part, and B is equal to 4 root 3, which is the imaginary part. Since A and B are got like this, we can substitute in this equation, that is A square root of A square plus B square. Square root of minus 4 square plus square root of 4 root 3 square. That is square root of minus 4 square is 16 plus 4 root 3 square. 4 into 4 is 16. Root 3 into root 3 is 3. So 16 into 3. 16 into 3 is 48. So 48 plus 16. So what is 48 plus 16? 48 plus 16 is 64. So square root of 64 is 8. So we got R as 8. So now we know that A is equal to R cos theta, which means A is minus 4. Minus 4 is equal to R cos theta, that is 8 cos theta, which means cos theta is equal to minus 4 by 8, which is equal to minus 1 by 2. Again, B is equal to R sin theta. B is 4 root 3. 4 root 3 is equal to 8 into sin theta, and sin theta is 4 root 3 divided by 8. That is 4 and 8 gets cancelled. It is root 3 by 2. So sin theta is equal to root 3 by 2. Sin theta is root 3 by 2 and cos theta is minus 1 by 2. So tan theta is root 3 by 2 divided by minus 1 by 2, which is minus root 3. So we got tan theta as minus root 3, cos theta and sin theta as root 3 by 2 and minus 1 by 2. So now we know that it is given that tan theta is negative, tan is negative, again sin is positive and cos is negative. The only quadrant where cos theta is negative, sin theta is positive and tan theta is negative is second quadrant, that is this quadrant. And we know that sin theta becomes root 3 by 2 and cos theta becomes 1 by 2 in theta is equal to pi by 3. So theta is equal to pi by 3 satisfies cos theta is equal to 1 by 2, sin theta is equal to root 3 by 2 and tan theta is equal to root 3. But the signs, the quadrant which satisfies all the signs here is second quadrant, and therefore we will take theta as pi minus pi by 3. So pi minus pi by 3 is 3 pi minus pi by 3, that is 2 pi by 3. And we know that 2 pi by 3 is an angle which lies between minus pi and pi. So we can write the polar form as Z is equal to R into, that is 8 into cos theta, that is cos 2 pi by 3 plus I into sin 2 pi by 3. So this is the required polar form of the given complex number. So we have discussed what is Argand plane and what is the geometrical representation of a complex number and what is the polar form of a complex number, and we have discussed two problems related to it. That's it. In the next class we will solve exercise 5.2. Till then, wait for the next video. Thank you for watching. Bye bye.